welcome. In this lecture, I want to go through a justification of the p-test. There's two real reasons to do this. One is just it's really cool that I can actually go through the entire justification of this formula using things that you already know. The other part is it's great practice with these things that you already know. So it's good practice with improper integrals and limits and all of these things. So let's just get started. So suppose that we have, so we're going to start with, so suppose that we have that a is greater than 0. Okay. Then our task is going to be that we're going to want to find the integral from, and we're going to start with 0, which I'm making red because this is kind of where the improper part's going to come in, to a. So this is that same a is there. Maybe I can even just kind of emphasize it a little bit with, right? So we have that a. Actually, that is the scheme. I think you're going to have trouble seeing that other blue. So we're going to write like this. So suppose that we have, okay, that this a is greater than 0. Okay, and then our task is to do this integral of, and then we have 1 over, and so 1 over x to the p, and then this is going to be dx. So let's just kind of draw the picture to help us a little bit to understand why this is an improper integral and what's going on. So we have, we're looking at the integral where we have, so we have, here are my axes, okay, and I have my graph. I'm just going to look at the positive part because we're definitely only dealing in the positive train here. So this is going to be x equals 1 over x to the p. I guess I didn't label my axes here. This is my x-axis. This is my y-axis. I have this value a. And then I'm looking at this area. So I'm looking at this area here. Right? But I'm right, but like, because I'm trying to get at 0 here. But the problem is you can tell the function goes off to infinity there. So what we're going to want to do is we're going to want to approach 0 from this side, and we're going to have this value t here. Okay? And you're going to be looking at, from this t, you're going to imagine that you're looking at this area and it's going closer and closer. So we're going to want to approach 0 from the right-hand side. Okay? I think that t is a little tricky to see, but hopefully you can get the, maybe if I make it another color, that you could see that that t is kind of there. Okay. So let's just get started. So we have the first circumstance we're going to look at. We're going to need to look at these circumstances differently. So the first one is what happens if p equals 1. Then in this circumstance, we're going to have the integral from, and then I'm going to go from 0 to a of, and then I have, so I have 1 over x to this p. dx. Okay, and this is going to equal the integral. So I've got the integral from 0 to a. Well, my p equals 1, so this is actually just 1 over, or dx over x. So it's 1 over x, so I can just write this as dx over x. Okay. Now I have this like pesky bound here, so I'm going to want to do the limits. This is going to equal, so I've got the limit as t approaches 0, and we kind of talked about why it should come from the right-hand side of, and then I have the integral, and now I replace, write that 0 with a t up to a of dx over x. Okay, and we already kind of know that this is going to equal, we would know how to compute that integral as being equal to the natural log of, so this is going to equal, so we still have to remember each time to write our limit. So this is limit as g approaches 0 from the plus side, and then we can kind of evaluate here. So I have the natural log of the absolute value of x, and I'm going to go from x equals t up to x equals a. Okay, and then, so then we'll close this off, right? But I can keep going with this. So I can put in these bounds, right? I want to wait until I'm as close to the end as possible, right? Because I wouldn't actually know how to compute that limit at this point. So this is going to equal the limit as, so I still want to say, you know, I still want to be writing my limit, but I can put in these bounds into here. So I have the natural log of the absolute value of a minus, and then I have the natural log of the absolute value of t. Okay. So now I can kind of look at these, and what do I know here? So I know that this, right, is going to be finite. Right? It's just, you know, this is finite. In fact, it's the natural log of a. But this part here, right, is going to go to, right, so I have t is approaching 0. And this is one of these things where from the positive side, right, and this is where we remember that, so let's kind of maybe put this in a little box for ourselves over here. So we have the natural log of, if I want to say that the natural log of t, and I know that this is like a little bit bogus what I'm doing, but we're going to bear with it anyway, is equal to 0. Sorry, the natural log of, I meant to write the 0 over here, so the natural log of, so I have 0 is equal to y, right? I should think of that as e to the y is going to equal 0, right? So how do I do that? I make y go to really big, like really big negative, okay? So this is kind of like my cheat work over here, right, that I would do in order to figure out that this is going to go to negative infinity. Right. So that's going to tell me, right, which I got from my cheat work over there. So this is going to tell me that this limit is going to equal positive infinity and is going to diverge. Okay. So what I've done so far, I run into problems. We kind of talked about this at 0. So I have to approach from this side. So I replace that 0 with a t. I take the limit as I go towards there. This is an integral I know how to do. I wait to take my limit until I'm actually going to be able to compute it. And then I'm going to take, so I'm going to have, right, so then I'm going to put these in here, the bounds in here, and now I can actually compute this, and I'm going to compute this by taking, I know that this one is finite, and this one is going to say about the natural log of t. And so I need to look at that by looking at what does it mean for e to the y to approach 0. That means that y's got to get very big negative. Okay, and then this diverges. Now, so let's look at the circumstance if p does not equal 1. So if p does not equal 1. Okay, so then we're going to have that we have the integral. And it's going to go from 0 to a of, and then we still have that this is, so this is 1 over x to the p. But now the p doesn't just drop out, so it actually kind of is playing a role here. So, and this is going to equal, and again, we do the same thing, right? Because it's not, this function is not actually defined at 0, I need to really look at this as a limit as t approaches 0, and we want to come from this side to a. Oops. I forgot to write the integral part there. Of the integral from t to a of, and then I have 1 over x to the p, and then we have dx. Okay, and so this is going to equal, and we're going to rewrite this in a way where it's easier to integrate. So I'm going to take, this is going to equal, so I've got the limit as t approaches 0 from the right-hand side of, and then we have the integral from t to a of x. So I have x to the minus, and then we write it like this so that it's easier to see how to integrate it. So dx, right? And then we take, so then we actually kind of integrate this. So we're going to get that this is going to equal the limit as t approaches 0 from the right-hand side of the integral from t. Oh, I had wanted that to be in blue. Okay, so from t, oops, at this point I meant to have integrated it. Okay, of, and then we have here, so we have x to the, and then we have, so we have that minus p, so minus p plus 1 over, and then we have minus p plus 1. Right, just like we would do with any polynomial. And then we haven't evaluated it yet. We remember to wait to evaluate until we do actually know how to take the limit. So we're going to go from t equals, sorry, from x equals t. For some reason I'm making a lot of typos. So from x equals t up to x equals a. And then this is going to equal the limit as t approaches, right? We're going to keep going until it's going to be clear how to take the limits. But in this case, we actually have to leave that because it's going to be different in different circumstances. So we'll go through that in the next video. But we're going to get this a to the minus p plus 1. Okay, divided by so we have minus p plus 1 here, and then we have minus, and then we want to put in t. So the t is in red, so I have t to the same thing here. And this is going to be minus p plus 1, and this is going to be minus p plus 1, like this. Okay, and then we have, so we're going to want to consider, so this is as far as we're going to make it in this video, and then we'll finish in the next one, because now we need to break it into 2 cases. Okay, so we're going to need to consider p greater than 1 and p less than 1 separately in the next recording. So, right. So we've got here these two circumstances where we're not, we're trying to avoid uh, evaluating something at zero that can't be evaluated at zero, but we can still take this limit. And we're just using these methods of integrating we already know because, and then doing the limit at the very end. So the limit doesn't come into play actually until the very end. Up until then, you're just integrating exactly as you know how. And this one we got the diverged using kind of what we know about the natural logarithm and its relationship to exponents. At least that's how I have the easiest time knowing how to take those limits. You might have other ways that work better for you personally. And then in this circumstance, we get all the way to here, and then this is not something that's going to be consistent. It's going to matter whether p is greater than 1 or less than 1, and so we'll handle that separately. Okay, so I hope this made some sense and that you're kind of enjoying being able to see that you actually have all the tools you need to prove something like this or to verify or to figure out something like this. And I will see you in the next lecture.